Hey everyone, thanks for joining us today. My name is Namdi Iregbalem, and today very excited to be joined by Satish Chandra. Satish is a principal engineer at Google, where he leads work that really sits at the intersection of AI and developer tooling. Satish is really one of the very important thinkers at Google in terms of how to apply all of the incredible potential benefits of AI to actually making software engineers more productive. Prior to Google, Satish was an engineer at Meta, at Samsung, at IBM Research, and even Bell Labs, all the way back in the day, which is very impressive. Satish received his PhD in computer science from the University of Wisconsin-Madison. And when he has time, I'm not sure how he has any time, he also lectures in computer science at Stanford. And last but not least, Satish is also an ACM, Association for Computing Machinery Fellow, which is a very prestigious designation and really speaks to Satish's many contributions. So, thank you so much, Satish, for joining me today. And did I miss anything from that introduction?
No, Namdi, that was overly generous. Thank you for having me. I always enjoy talking to you, so I'm excited about today's conversation.
Yeah, me as well. Satish and I met. I was actually looking at our email threads. Originally, it was almost exactly 2 years ago as part of a reference call that I was doing on a founder that I was considering investing in. And, we did make that investment, so that worked out. And, Satish and I have stayed in touch and just love to trade notes on, everything that's happening at the intersection of AI and software engineering. And so for this conversation, you really wanted to center it around, those exact topics. Satish has published a lot of research in this area as part of his work as engineering leader. And the two papers that we wanted to cover today, the first is called Evaluating Agent-Based Program Repair, and the second is called Agentic Bug Reproduction for Effective Automated Program Repair at Google. And so I thought we could start off with that first one. Why don't you talk about what the aim of this research was, or maybe even the kind of spark that ignited it, and what you were trying to accomplish?
Yeah, absolutely. Yeah, thanks for taking a look at these papers. So this one is about to appear in ICSE International Conference on Software Engineering at the end of this month, at the end of April 2025. The conference is in Ottawa. So for those of you who see this before the conference, please come to our talk. Now, how this paper came to be, we obviously were investing in LLMs. We continue to invest in LLMs and all kinds of applications of LLMs to software engineering. We have done, as you might have seen from our previous blog post, a lot of work on code generation where you are sitting in an IDE typing along and the AI produces what you were thinking of typing next. We have done work on resolving code review comments and things of that nature. But then over time, people start realizing, well, okay, this is all happening more in the so-called inner loop as you are developing code, but there is a lot of potential in using AI techniques for outer loop, by which we mean debugging, especially, production bugs that are sitting in bug databases, and so on. And I think historically less attention has gone into those kinds of applications of AI, but it's beginning to catch up. Now, also, a while ago, we heard a lot of excitement about, sui bench and agentic techniques and things of that nature. So as these developments come in our ecosystem, we also take a look and see, how well or do these work in our context. Let's give it a try, right? And so with all of these things, we don't know ahead of time whether this will work out or how well it will work out. So it started as just an exploration that let's take simple ideas in how people are talking about agents in the context of software and take bugs that we have in the company and see what would it take if you took those bugs and try with these agents. Nothing fancy, but let's get started and see where we go. And so that's where this is started. And now we can dive kind of deeper. I'm sure you have questions in mind that you want us to talk about.
Yeah, that's a perfect setup. And you wanted to kind of first dive into, I think, something that's kind of interesting topic area, which is maybe some of the differences between, the paper talks about Google's internal issue tracking system, which you abbreviate GIT, and I have to assume that abbreviation is on purpose. So Google's internal issue tracking system, and one of these very common benchmarks, SweBench. Maybe talk a bit about differences between those. SweBench is very common these days. It's kind of one of the go-to benchmarks as people are trying to test the performance of these systems on coding tasks. So just at a high level, talk about some of the differences there.
So that's a great question, and we actually did not start this work intentionally trying to tease out these differences. We wanted to start somewhere, and as is customary, we want to start with setting up an eval set drawn from our internal bug databases and go with those. But as we curated this set, we were obviously inspired by how the SweBench paper talks about how they curated there, right? So once you look at that and you have your own curation, then you become curious, okay, let's see, are there remarkable differences between these two? And so we had a look. So one thing, as many people will know about SweBench, is that it is centered on Python, and it's drawn from a small number of GitHub repositories. And to the credit of SweBench, this really started a lot of follow-up work. So, it galvanized the community in trying agentic techniques. Okay, so when we look at our internal databases, obviously these are multilingual. We see not just Python, we see a lot of C++, Java, etc. And so we really need to reflect our eval set in a way that the language distribution in our bug database reflects. So that is one difference. Then it becomes also like, okay, what about difficulty levels? Because we are not particularly going after the team looking at internal deployments of AI-based techniques is not particularly looking to address SweBench as such. But when we look at these kinds of benchmarks, it's useful to see what are the differences in terms of characteristics. So we see that, okay, in terms of localizability, one of the things you need to do is to see, is there information in the bug report that helps you get started? How much is that information? So typically identifier names, file paths, things like that. These are good clues that will let an AI agent to get started on the journey to fixing these bugs. How prevalent are these? Sometimes we see that these are plentiful. Sometimes we see these are pretty sparse. And that's the localization signal that we have, it's in the paper. We see that there are some statistical differences there. There are statistical differences in the size of patch, in the distribution of patches across files and things like that. So these are signals. It does not mean that the results that we compute can be just directly compared against SweBench results. By no means it implies that. This is purely a study on characteristics of these two benchmarks. So I don't want to imply more implication than that.
Yeah, no, very, very helpful. In the paper, you kind of have this interesting kind of schematic for how you filter down into what ends up in the evaluation set. And it's important, right? Because I think, in other areas of kind of scientific research, you do need to talk about, how did you end up with the set of things upon which you tested? And I think sometimes we forget about that in the AI context. So I love the rigor here and just kind of showing how these decisions were made. And so, you get down to this, eventual data set. And then you talk about in the paper this sort of, agentic system you built called Passerine, if I'm pronouncing it correctly. Maybe talk a bit about, I think there was a diagram down here about the kind of approach. Like, how did you design this? Everyone's talking about agents these days. It's a big topic. The sort of design space for agents is very wide. Maybe talk about kind of your design methodology and maybe even any advice you might have for other people who are building, agentic systems.
Okay, so first of all, this design, I would not want to claim it as our invention as such, because prior art in particular, we talk about SweAgent. That was a paper available before we got into this business that essentially talks about this, that you collect a set of Unix style commands. For example, you can cat a file, it shows you file content, or you can list the contents of a directory, etc., etc. You can run some tests and so on. So with a set of these kinds of commands, you can then take that and use that in what is now called in the community a React style loop. And what that is that you start with some context. So typically this would be your bug report that you start with and some system instructions. And then the LLM will be encouraged to produce some thought and decide which kind of tool or Unix command in this particular case it wants to invoke and with what parameters. So then it dispatches into a sort of a runtime which will actually run that command for you. And this is the cool thing, that you are allowed to actually run some of these commands in the system. You do that and you get more information from the environment that you did not have before. And that information becomes part of your context. And then the LLM can look at that additional information along with what it had before. And then, so that's your sort of observe part. And then you go back and think what you want to do next. And it turns out that with this iterative journey, you sort of begin to understand, okay, for this kind of issue, I need to see this. This file must be the one that needs editing, or maybe this set of files. And then you issue some editing commands. And in the end, you have produced yourself a patch that modifies one or more files. You have to test it, and then you are done. So this is the basic scheme. It was discussed in the SUI agent paper as well. A lot of other work that I am aware of essentially follows variation of this scheme. Some people have advocated to orchestrate the diagnosis part more explicitly before you get into editing part. We chose to let it go, and in our empirical observation that seems to work out. But there are many variations possible here. A lot of variation happens in the space of which tools to use. A lot of variation happens in the space of how much history you keep around and what you show to the LLM for each call. So there are all these variations in the design space, but what I described just now is kind of like the basic template of how you do things.
It's tricky, right? Because even not just like which tools you give the model access to, but how many tools, like how long is that list? Because that affects.
How long is that list? Yeah, and this is also an interesting point. Thanks for reminding me. So there are some basic commands that were listed in the visual you just showed, but let's say you want the tool to have access to another repository of documents, or the tool might have access to some kind of historical logs or something. So if you think that is beneficial, you are not going to pack all the information in the LLM ahead of time. You want to dynamically fetch some of that information and add it into the context. And so then it becomes a question of what are the sources of those information, what tools do you need to bring those information in, and so on. So there is a lot of space for creativity. I think this is kind of a very exciting area, which tools to use, how, and so on. And also the tools, just they are interesting things. They are very valuable, but they also need to be used carefully, because otherwise your agent can go in all kinds of directions, just invoking tools and not find its way home.
Yeah, it's a very relevant topic these days with everything happening around tool use and these agentic systems, and people are really putting these things to the test in terms of how many different tools can they even sort of reason about, and then the responses come back, and what do you do with that, etc. Yeah. I wanted to also ask about, one of the things that you note when it comes to, the actual results here is this sort of performance gap between machine reported bugs and human reported bugs.
Yes.
Maybe first off, just make that distinction more clear. I think a human reported bug is intuitive enough, but for folks who aren't familiar, what is a machine reported bug?
Okay. Yes, so very, very pertinent question. And we have a diagram with some pseudocode in the paper if you want to bring it up while I talk. Yeah. So in our company, at least, there are these sort of monitoring jobs that are, this one. Yes. So so we picked two kinds of bugs. The first one is about sanitizer bugs. So they, for example, look for memory related error. Are you writing to the right address or things of that nature? And these processes keep running, and they will suddenly realize this other process that I'm monitoring essentially has this kind of memory badness. Let me create a bug report for it, and it will try to leave behind some reproduction information and some characteristic like what it thought, what was the stack looking like at that time, etc., etc. Right? So roughly speaking, that's the nature of these bugs. The second one, this test auto dependence bugs, again, this is more specific to testing, and it says that, well, sometimes people write test cases where they inadvertently create dependence between test cases. So things work if they run in a certain order, but not if they work in a different order. And so this one tries to mix up these orders a little bit and expose one of these test dependence or order dependence issues. And this will also, it will run automatically. It will create a bug report. You can now, many of these are created. And so an interesting problem for us is that can we use AI to actually resolve them, right? So this is why we look at these machines, and these are not the only two systems. We have more that can generate this, and we fix it manually. But for us, as AI matures, we also want to see if AI can fix these things. Now, why are they easier in a way compared to human filed bugs? So a couple of reasons. First of all, these come with reproduction tests more often than not. So for example, the test order dependence, one can say that, okay, the specific order that did not work out was based on this seed and this order. And so that information in of itself becomes a reproduction test where we can use the same seed and replicate what happened. These machine generated bugs also come with a lot of file paths and identification name and excerpts from stack traces and things like that. So it's a pretty rich bug report that gets filed. That makes it easier for the AI, if nothing, to begin to localize, because there are so many clues in the system that you can get started. Now, human beings, when we file bugs, we are encouraged to be comprehensive, but everyone is busy. We sort of sometimes write terse bug report. We may not give enough clues. We typically don't see hints about how to reproduce these bugs, etc., etc. For a lot of work, in fact, a regression test is added at the time the bug is fixed, as opposed to at the time the bug is created, like a failing test is not created. So for all of these reasons, we just find machine generated bugs for agents to be a little bit more approachable than human filed bugs. Human filed bugs in some sense have a broader spectrum, more variance, and so on.
Yeah. I'm curious what implications you feel like that has for, the future of AI-driven software development.
Well, yeah. So for one thing, we probably want to provide tooling where when people encounter bugs and they capture the symptom of the bug, that gets captured in a way that records more information, and that will immediately help automated bug fixing from that, right? The other implication, and maybe I don't know if you were specifically going in that direction, is that if the cost of fixing these monitoring or machine generated kind of bugs can be made to trend down, as will happen with AI, then in some sense that's a huge relief, and we can in fact run these kinds of software reliability processes without creating a lot of human overhead with us. So you can say that it in some sense reduces the cost of keeping your software reliable. And it's like you can think of it as trending towards a self improving system, right? Where there are processes that try to discover problems using a variety of techniques, instrumentation, fuzzing, whatever you have.
Yeah.
But at the same time, as you create these problems, it's not like you are creating a backlog for humans to deal with it. You can also leverage AI to deal with that backlog. In the end, some human will have to sign off on fixes, but
Sure.
signing off is a lot easier than going off and diagnosing everything and so on. So I think if this technology succeeds and makes progress, we can see this kind of like a self-improvement loop kicking in a bit. We are not obviously immediately there yet, but that's a trend that I'm seeing.
Yeah, it's something that, I've talked with some other folks kind of working in this space, is this idea that in some sense, tests and, bug reports, etc., are almost like the killer app for an AI software engineer, or the reverse, that, AI software engineer is the killer app for tests and bugs, because you can then kick off that, self-improvement loop, which is really interesting.
Yeah.
And then, one thing that's always interesting when we think about agents is sort of looking at these trajectories that they take, and it can be interesting to just dive into these and just sort of see where is it
interesting.
where is it smart, where is it dumb, where is it going off track, etc. What are the landmines, etc. I don't know if there was anything that stood out to you as you all were sort of looking at the results here.
I mean, as you can imagine, this is something that we take extremely seriously, and most of our time goes into looking at what happened and how we can prevent bad behaviors from happening and encourage good behaviors and things like that. I'll say a few things. I think there is one thing you can do is think about what you are optimizing for, right? So let's say if your goal is to solve a given bug, and let's assume that it is a economically good idea to solve that particular bug, right? Then you want to spend more resources, more cycles, and do whatever it takes to try to fix the bug. A different application could be that you have like a pool of bugs, and in some sense, some kind of limited compute resource you want to use to attack that pool of bugs. Now, this is a different problem, because now you have the flexibility to say that I'm going to use my compute resource where it makes sense, right? And not waste compute. You could also, if you had unlimited compute, you could create many trajectories, and then you try to rank those. If you have limited compute, you will use fewer trajectories. You want to kill the trajectories that don't look very promising, things like that. You may have to have heuristics which decide if a trajectory looks good enough, I'm just going to go with that and let the human decide what to do afterwards. So there is a lot of economics that you can think about as how much exploration you want to let AI do before it finds good trajectories, because in the end you probably don't want to waste compute. So that is one way we look at it. Second way we look at it is that human time is precious. So as we are collecting multiple trajectories, and some of them may claim that, oh, I look good, I seem to have fixed the bug that was previously triggering failure, right? And some other trajectory says that, oh, I also look good, I also have fixed this, but my fix is different. And so you can have like a number of these. All of them can be wrong, because simply shutting down a failing test is not a certificate for the correct fix, right? Now, a human faced with these many candidate trajectories and their fixes has to spend cycles. You want to invent techniques that optimize for human attention there, because you don't want to throw all these things. Otherwise you are generating more homework for the human. So we want to have these ideas where we can use human time in a very economical way, so that you look at a few things and you feel like, okay, maybe not everything that the machine did was right, but it was almost right, and by my net time investment is a win. And so that's where this whole trajectory analysis and trajectory management comes into play, that you want to be smart about how you engage humans' attention.
Right.
Yeah.
Yes. As maybe compute becomes less of a constraint,
Yes.
human time still remains a constraint.
Yes.
So you need to economize on that.
Yes. Absolutely.
For
Absolutely.
sure. I want to ask one more question about this paper before you switch to the second, but I wanted to backtrack slightly and just share the the difference in performance between the machine reported bugs and the human reported?
So here, this chart, let's say the top one, right? Like this shows a higher success rate on the sort of blue and orange curves and lower success rate on the green ones, which are. And so here, yeah, so this is what, so with the blue ones, these are the sanitization ones, and the orange ones is the test order dependence one. And you see that the fix rate, in some sense, how the for percentage of things we can fix is better in machine filed bugs, because we have more to go with. But one thing that is interesting, if you see the gap between the two orange lines, right? So the test order dependence bugs, you can get the system to claim that it found a plausible looking fix, but the actual whether that plausible looking fix was valid from the human eyes, that drop is fairly substantial. So you can see that from the charts, and that's because the reproduction is only talking about fixing these things for a particularly chosen order. But if you fix a symptom for a particularly chosen order, that does not mean you have fixed the general problem of being, there being interdependence between tests. So when we as humans, when we look at what the AI produces, say, oh, no, this is trying to overfit for that particular order, and this is not a true fix. And this happens a lot. So this is actually a good point, like how one of the challenges in this system, in this whole space is, again, can we have tests or ways of validation that are strong enough where we as humans don't have to spend this much time trying to tease out, well, did this suggestion work properly or not, and things like that, because that's where a lot of human time goes. And this relates to the point that we just discussed just before this chart. Now the human ones, the green ones, the interesting thing is that the two graphs there, the one with the dots and the one with the x's, they are actually close
Very
to
close.
one another.
Yeah.
So while they were difficult for the AI to solve, but the solution, when it found the solution, happened to be reasonable more often than not. And this wasn't the case in the machine files. So interesting dynamics. We'll learn more as we go. This is kind of still only early days,
Yeah.
but interesting dynamics.
Very, very cool. I guess lastly on this paper, any implications for automatic program repair that this work kind of takes you to, or maybe kind of where do we go from here in this space?
Yeah. So I think we already touched upon two or three things. So first of all, like I think we should kind of not get ahead of ourselves here. We still have ways to go in this technology. One is this problem of like patches that are produced that are not true fixes, right? And this problem is encountered by everyone. This problem, incidentally, Namdi, predates the LLM based fixing era, because in software engineering research community, this business of automated program repair using variety of techniques, combinatorial techniques, genetic programming, this, that, there have been many attempts, and everyone finds this, that okay, the system finds a plausible patch, but that's not correct patch. And that problem has not gone away with the advent of AI. So I think for the research community especially, this is still an ongoing challenge, how to deal with it. Second point that we also touched upon a little bit is that the exciting part here is that we are creating capacity in our system by relegating a lot of this diagnosis kind of work to AI. And so this can help towards sort of self-maintaining, self-healing, whatever someone will come up with a cool name for this kind of thing, but you know what I mean, right? Like that. So that I think that trend, we are trending in that direction. Third thing is that, repair, I feel, is one kind of application which we tend to latch on to. But really, if you think about it, the technology for repair is not that much different from technology that may be needed for a more general task that's not just about solving bugs. So you as a programmer might say, okay, I'm working, I'll leave this to do in my code and I'll move on. And I kind of know how to do this to do, but won't it be nice for some AI to come in and do that to do for me autonomously, and I just need to kind of look over and see if that works, right? How would you approach this kind of problem? To some extent, you could use agentic solutions, essentially, to find the problem, try to generate some tests, etc., etc., try to fill in the details. And I think in that kind of code generation scenario also, there could be a lot of potential. You also might have seen this work called Lancer, where people are
Yes.
talking about, creating, getting AI to solve all these tasks. So I think that a lot of interesting technology is being developed for program repair, but what we are learning in our journey will also be helpful more broadly.
Very good. I'm excited for whatever cool name they come up with. My bet is on like Andre Karpathy or somebody coming up with something. I mean, he coined vibe coding, and now that's become like it's basically in the dictionary at this point. So
At this point, yes, yes, yes. And maybe we should check with Andre if he has a suggestion.
yeah,
Yes, very good.
yeah. Okay, and so let's talk about the second paper, agentic bug reproduction for effective automated program repair.
Yeah,
At Google. One thing that would be helpful. I mean, we're already kind of on the topic of
yeah,
automated program repair.
yeah,
But one thing that'd be helpful just as far as like defining terms, there's this important term in this paper, bug reproduction tests or BRTs. Maybe start off with kind of explaining what those are and kind of how that relates to
yeah.
the point of this
So
work.
yeah, yeah. So essentially you want like a signaling test in some cases that fails before the fix and passes after the fix, right? So that's kind of, we can call it as a bug reproduction test. Now, in the context of program repair, you might want to assume that such a test is always available, right? But sometimes it is not, for a variety of reasons. We touched upon this a little bit. Humans don't always create a bug reproduction test when they create a bug report. Sometimes the culture is that when someone fixes the bug, they will actually submit a test at that time which watches for regression. And that, in retrospect, you can think of it as a bug reproduction test, because if you were to roll back the patch in the code and still run that test, presumably that test would fail. But going forward, at the time the bug is filed, such a test may not be available. And so there is an attempt to generate this kind of test, because it helps validate whether what the patch you generated using AI is reasonable or not. So that's the kind of the brief overview of the terminology here.
Great. And then maybe talk a bit about what you're trying to accomplish in this work,
Yeah,
at a high level.
yeah, absolutely. So, I mean, bug reproduction tests, or BRTs, are kind of interesting end products in their own right. We have colleagues in the company who say, okay, oh, cool, you can generate a bug reproduction test, or that itself is valuable. But
Hmm.
we came into this business through our work on trying to use agents for bug fixing. And so it turns out that this kind of a bug reproduction test was basically essential, because when you go from machine filed bugs to human filed bugs, they didn't come with those often. In the eval set that we reported in the ICSI paper, we sort of backported those kinds of bug reproduction tests from the actual fixes. At that time, those tests were added, right? But in terms of open bugs, where those bugs don't have a patch or a BRT submitted yet, if we want our agentic technique to address those unsolved bugs, we need some way to quality control before we can show a patch to the human. We don't want to just waste our colleagues' time, right? So bug reproduction test generation was important for us. It now also coincidentally turns out that if you create this bug reproduction test and you show it to the bug solving agent, then it can actually benefit from knowing a potential bug reproduction test. And this is something that is in the paper that can help the fix rate. Also, earlier we were talking about, how multiple patches can be generated, and you need a human to look through many of these. So it turns out that you can use the bug reproduction test also to sort of at least do a first pass of triaging between those multiple trajectories. So it turns out that it has multiple uses, and it just seems like a good idea to try to do this.
Very helpful. And one of the things that in this paper you use is you've taken an LLM and I think particularly fine-tuned it for code editing, as opposed to maybe using something off the shelf. And so I'd be curious kind of why you did that, or sort of why that was kind of the appropriate choice. I mean, obviously fine-tuning on code editing would presumably make it better at code editing, but what were there other reasons why you did that?
No, so this was like we go back and forth. We actually use out of the box models for planning and as much as possible for editing and other things. Sometimes, as you can imagine, these models are trained generically on more public code, right? And so on. So let's say your company uses a certain test framework.
Mm-hmm.
A public LLM might not have seen that test framework, and so if it needs to spit out code that is compatible with that particular test framework, what are your options? Well, you can include in the context some examples of how the test framework code looks like, and then the LLM might pick up on that. Or you could lightly fine tune this with examples of these specific kinds of tests and so on. So sometimes there is value in creating awareness of a certain code repository. That awareness can be implemented in multiple ways, through context or through fine tuning. So in this paper, we chose to do a bit of fine tuning for that. And for the patch generation, or in this case, BRT generation, it seemed to be helpful. But I think there are multiple ways of doing these things.
I always find it interesting, typically when these LLMs, a new LLM comes out, or someone wants to try their performance on one of these benchmarks, you kind of have to separate, the kind of LLM alone plus like LLM plus some kind of scaffolding.
Yes.
Or maybe the LLM fine-tuned on the, and I think these end up being kind of important differences.
Yes.
A model that is assisted by scaffolding is one thing. A model that has been fine-tuned on something is another thing.
Yeah, absolutely. And these differences will show up as we. So in the end, if you need some specialist piece of knowledge that the model just did not know ahead of time, you have to communicate it somehow, right?
Yeah.
That's one thing. But a lot of other things, it's scary how, as LLMs are going through generation and they are learning reasoning and thinking and all these skills, if you see some of the the way these LLMs are articulating what they are doing as they are solving a bug or something, it is pretty impressive. So I'm very optimistic that these things will work well.
And then one other thing that could be helpful to define here. So you create this ensemble pass rate metric, kind of evaluation metric. Maybe talk a bit about that.
Yeah. Okay. So this refers to the point that we were talking about, like what are these bug reproduction tests good for? And one of the things I said that, well, if you have multiple trajectories, then you can actually use these to triage from them, right? So now think of, if you have some number of trajectories, it's kind of like a ranking problem, right? Like how do you know which one is better? Because you don't really know ahead of time. It's all past something, or maybe there wasn't any test and now you have to make sense of it. And so our thought was that, okay, BRT generation is also not perfect, fine, but let's say a separate run of the LLM says that, okay, here are some small number of BRTs that it thinks based on some other criteria are reasonable, right? So now you can say that, well, one way to assign a score to a trajectory is that how many of these BRTs pass on this plausible patch, right? So that
Hmm.
gives a score. And now you can use that scoring system to essentially design your own way of figuring out what you want to show to the human. So you may decide that, okay, I am going to show anything that has BRT pass rate above a certain threshold, or I'm going to show top three based on that scoring and so forth. So that's really what this ensemble pass rate metric is. I think there are many ways of designing this kind of. It's basically a ranking heuristic based on what you can learn from BRTs and what you want to show to the human.
And then maybe we talk a bit about some of the results from the paper.
Mhm,
You have a couple different things that you talk about.
mhm.
Let me bring up the paper.
So yeah, so there was like the paper had maybe three kinds of results, and so the first kind of result was before we got started into this thing. There were some earlier papers, or there was one at least that said that okay, we are going to make one call to an LLM, give it the context, and have it generate a BRT. This is, you can think of as a pre-agentic approach,
Yeah.
and compared to that, this one, our approach worked better. Perhaps that's in hindsight not super surprising. Now there are other sort of concurrent works that if you look around, there are works published by, for example, our colleagues at IBM Research and elsewhere that are also trying to use agents for generating these kinds of tests. But anyway, the result here was that compared to one shot generation, this works better. So that was one. Second was, I think we had a table somewhere that showed that if you did give a BRT to Passerine, and that was kind of our original motivation. Yeah, so here the overlapping when
Yeah.
this Venn diagram kind of thing, right? So with the BRT given, Passerine was much more successful in finding a right fix compared to when BRT is not given. So the when BRT is given is 17 cases and not given is 13 cases. So it's not a very large scale experiment, but early indications, at least out of a data set from 23 cases where we had validated BRTs, this is what we found, right? So that's second result. And the third result is, it's a little bit harder to read, but it's in this histogram type of chart that is
Yep.
shown here. And what this is essentially saying is that when you provide a BRT, then the number of steps on an average that the agent has to go through to find a patch is smaller. So that's good because then you have shorter trajectories and you don't spend as many calls and as much compute. So these are sort of roughly the three main quantitative results that we have in this paper.
Yeah, very helpful. And just for ease of interpretation, so this chart, it's the distribution with the BRTs is kind of shifted to the left, where this
It,
axis is
it
the
shifts
number
to
of
the left,
steps.
exactly.
Yeah.
Exactly right. Yes. So the distribution shifts to the left, and so you finish the same amount of work in fewer agent steps.
Just thinking about this paper and the results that you achieved, I'd be curious, almost like what here was surprising to you, because to your point, certain things are probably less surprising, but I'm curious, like what things were actually surprising even to
Okay.
you as you.
Yeah. So for me, and this may be an opinion that is more me than everyone agrees, the agent figures out the order in which it should do things. That
Yeah.
to me was very exciting, right? So we have in that previous paper, the first paper that you showed, there was this chart with multiple colors on each bar, and it's showing like how many calls it's using for cat, which is reading files, and how many calls it's using for editing. Yeah. So this is actually this paper, but
This paper, yeah.
but if you look at the other one, right, evaluating one, and you scroll down a little bit, yeah, here also. So you see, let's just look at the left one, right? Initially, so the orange segment of the bar is showing the calls to code search, and the
Yep.
blue ones are showing calls to cat, and the green ones are showing calls to edit. So what is to me pretty cool is that initially in the initial steps generally the agent will use code search and cat to sort of learn and feel its way around what's going on and so on, and it's not start editing right away. But once it has formed some hypothesis, and it's important not to anthropomorphize these things too much, but as as it has figured out what may be plausible cases to fix, or possible reasons, or hypothesis, or whatever, then it starts doing less of this cat and code search and starts doing more of editing and so on. And you can see this kind of behavior on human bugs also, and the two kinds of machine bugs. Why should this happen? So this to me is a very interesting thing that emerged, because you might be tempted that, oh, how would the agent know what to do, and so maybe we need to bake in an explicit orchestration of what to do. Maybe that will work even better, but out of the box, just this purely self-determination of what to do next actually doesn't work too badly. So to me, this was pretty cool.
Yeah, it is very cool. Do you interpret anything about the differences between for the human bugs or the machine bugs? Like I see this Blaze action, and I'm not exactly sure.
Blaze is about the
Yeah.
building and running tests. Yeah.
Okay, so for the machine reported bugs, it kind of goes straight to blazing, much
So
earlier. Yeah.
yeah, because it is trying to reconstruct the bug the way we set it up. It's trying to first ascertain that that bug can be reconstructed within this process. So it's trying to do Blaze to first make sure that that bug is still exists and can be reconstructed. So that's why you see that over there. Yeah. With human ones, as we say in the paper, we have a pre-tested sort of a bug reproduction test that we sort of snatch from the fixing patch, and we use that as the test finally. So we already know that it doesn't have to do that work.
Yeah. I also thought it was interesting in the second paper,
Yeah.
you have a kind of similar chart, slightly different,
Yeah.
action set, but between editing and testing, they kind of end up being reasonably balanced in terms of at any given step,
Yeah.
like how likely is it to edit
Yeah.
versus test.
Yeah.
Any thoughts on that?
Not particularly. I think it's just a curious empirical observation that they end up being. So the other thing you have to notice that the net counts are going down, which means that some trajectories will be shorter, right? Like we
Yeah.
don't run everything. So there is that. The typically, this just shows that how many times finish sort of took these many steps. So that's the dark green one.
Mm-hmm.
Why editing and testing typically have same number? It's kind of hard. I think this is for bug reproduction tests. So in some cases we see that you have behaviors where you have to do multiple rounds of editing if you are trying to roll out, let's say, something that touches multiple files, but then you will test only once. But in this case, it may be that you have like edit and then test in sort of reasonably balanced way. So maybe that's why this is coming out to be a pretty similar size segment.
Yeah, makes sense. Yeah, these are all in some sense like conditional distributions, like conditional on getting to this step. This is
Yes,
is
there's
done.
absolutely. This is
Yeah,
conditional to getting to that step.
yeah.
Yes. And initial things are always about, code search and looking at files. That's what it will do for a while.
Very good. But maybe just a last one.
Yeah.
And I'm being purposely provocative. I know you don't like to think of, I think as you were saying earlier, AI fully taking over from human, software engineers. But this is sort of the talk of the town right now, especially with all these AI software
Yeah.
development tools, growing very fast and being
Yeah.
adopted, very quickly. It is in some sense one of the top AI use
Mhm.
cases. And so maybe just like pontificate a bit about, the future of AI software development, when it will be the case that these things can really, in an automated way, kind of just be running autonomously on a code base. Is that soon? Is that coming soon? Is that not coming soon?
I think a lot of things are already being done, autonomously. Let's say, it's hard to pin down how autonomous, right? But if you look at the level of automation with which we are doing things already, it's pretty impressive. We have another paper out on rolling out code migrations using AI. You can find it easily. And that is, using AI to make large scale code changes that all of our, internal users need to do. So if you see the amount of automation that we are already leveraging, that is pretty significant, right? And it will continue to grow. In terms of how, maybe the question you are asking is that is human going to get out of the way or not? I think there are probably, some ways to go. What we are seeing is shift where human is becoming more of a reviewer. So you, instead of human writing code, human is reading code. So this could be code that you are typing something and the autocomplete produces a bunch of stuff, or like what we talked today about bug fixing, you are being shown a potential fix that is AI generated, and you as the human have the final authority to decide whether to accept that fix or not. And analogous cases like in migrations also, not just one place, but it might show you, here are all the places that I changed. Am I good to go? Should I land it and not? So we are using automation. We are not at the point where, at least I am not comfortable saying that let's just not even look at code and have these things landed. We need to be comfortable about this. I think there are policy and other matters to also consider here, because ultimately we want to be responsible software engineers and we want to make sure our systems are balanced. And there are all kinds of other implications. I'll throw one back out at you. If you imagine code that gets generated that goes into deployment without human oversight or without human massaging it or human touching it or whatever, right? What can happen with few iterations of model training on that code? So you could imagine, like, it's kind of like the code loses a little bit of its distribution and becomes a little bit more of a monoculture.
Yes.
And then it may be becoming more vulnerable to certain kinds of malfeasance and so on. So there are all kinds of interesting issues that, software development itself is leveraging automation. We have to be aware of what are our obligations in terms of being responsible about it. And I think this is not a settled matter, and I'm certainly not qualified enough to make a call here to say when we should be happy about letting software be fully autonomously developed. I think it's a community effort. We have to decide what's going on here.
Yeah, it's funny. What you pointed out of like this notion of, some people call this kind of like AI slop, but basically like AI generated content, basically polluting the future training data, of these AI systems.
Yeah.
The effects that could have. I remember GitHub back in, I don't know if it was 2020 or exactly when it was, did this Arctic code vault thing where I think they just took all the code and almost like saved it as it was at that moment. And I don't know, we'll probably look back in history and say that was like an important artifact before the AIs showed up. It is in some sense a very important kind of distribution.
Absolutely. It's an important balance. I think what you are seeing being in venture capital is that the economic potential that this is showing in terms of using AI for a lot of routine but increasingly non-routine things. I mean, that potential is huge, and the business community cannot ignore it. We have to leverage it, but we have to leverage it responsibly.
Great. Well, I think that's a great ending note. Thank you, Satish, for doing this. I really appreciate it. Again, I think your contributions have been, extraordinary in this area, and you're a very thoughtful thinker in this regard. And it's good to hear that you are not comfortable with vibe coding. This is basically my takeaway.
I don't think I can afford to be on the wrong side of Andre, but
Yeah.
I want to thank you for having me over, and also for actually reading through these papers and asking all these interesting questions. So yeah, thanks a lot, Namdi.
Of course, no problem at all. I love it. All right, thanks everybody for joining us. We'll see you next time.